Section 12.5, Lines and Planes in Space. So once again, here are our learning goals. You should know equations for a line given 2 points R3, or more broadly speaking, just know the general form how we define lines R3, be able to apply this equation. You should know the equation of a plane through a given point with a given normal vector in R3 in various forms, and given various pieces of information about the plane, do the above. So, the first half of this section we'll be talking about lines, then we'll switch over to talking about planes. Okay, so I think this is a worthwhile thing to think about, is how can we represent a line in R3? So we know that, like, if we have a line in two-dimensional space, y is equal to 2x plus 1, we might rearrange that into some kind of standard form, negative 2x plus y is equal to 1. So line in R2 is going to be ax plus by is equal to c, a constant. And so you might think that we might have something like ax plus by plus cz is equal to d would be the equation of a line R3, and that turns out to not quite be right. So, and later on in this section we'll talk about why this isn't right. So instead, let's ask a similar but related question, which is what information do we have? So if I were to have, so like this is some line in R3 up in three-dimensional space here. Well, I think that I have a point on the line. So right here is a point. Now you could say it's like 2 points on a line, and that definitely is true, but maybe a more fundamental thing here is that we can also think about the direction that the line is going in. And so as a example of this, suppose that our point on the line is, corresponds to the vector 1, 2, 3. That's the position vector of the point. Suppose that the direction vector is 4, 5, 6. The way that we end up representing our line in R3 is parametrically as r of t is equal, in this case, to the point 1, 2, 3 plus t times the vector 4, 5, 6. So r of t is the point's position vector, the point that we know about, plus t times the direction vector. So this is how we represent a line R3. This is a particular, let's say, particular example here. So let me do this a little bit more generally here. So in general, if we have a line through the point P naught, the position vector is R naught, and that's parallel to vector V here. R of t is R naught plus t times V. Let's say parametrization. We have to say what values of t this works for. This works for all real values of t. T runs from negative infinity to positive infinity. So if we go back here, going off in one direction would be t going to negative infinity. Going in the other direction would be t going to positive infinity. So this is one way that we frequently express things, through this vector equation. We sometimes write this out as 3 separate parametric equations, where we pull out the x, y, and z equations separately. So to go back to this slide right here, the x component would be 1 plus 4t. The y component here would be 2 plus 5t. And the z component here would be 3 plus 6t. So what we do here, x naught, y naught, z naught, 1, 2, 3, those are the coordinates of our point that we know about, plus t times v1, v2, v3, 4, 5, 6, those are just the entries of our direction vector, once again, we are going to have we're going to have our parametrization t, the parameter t is any real number. Okay, so this is the basics for what's going on here. Let's do a couple examples. I think this is maybe the simplest possible one. I gave you a point. I gave you a direction vector, so we can simply write down r of t is equal to the position vector for the point, -2, 0, 4, plus t times the direction vector 2, 4, -2. Okay, and t can be any real number there. This is it in the vector form. Let's do in the parametric form, x, y, and z. So x, -2 plus 2t, y is 0 plus 4t, z is going to be 4 minus 2t. Okay, so I think this is maybe about our simplest example I could give. So let's just make it a smidge more interesting. Let's find an equation of the line through 2 points. So once again, what information do we need? What information do we need to do this kind of thing? Point on the line and a direction vector. We have 2 points. We don't have a direction vector for the time being. So what do we need to do? We need to find a direction vector. We need to find a vector that's the vector from, so let me maybe draw a picture here where there's P2, there's P1. So we are working on finding this direction vector. How do we do this calculation? We just subtract the corresponding components. It's so 0 minus 2 is -2. 5 minus -1 is 6. 4 minus 7 is -3. So at this point, we can write down our parametrization r of t. We'll just use this first point P1. So 2, -1, 7, plus t times -2, 6, -3. And as always, I'll just go and write down all t, all real t. So again, fairly straightforward example. It just emphasizes the need to have a direction vector and find one if you don't have one. Before I do one last example in this video, I want to highlight an important fact here, which is parametrizations are not unique in general. So what we know that we need a point and a direction vector. I chose to use 2, -1, 7, but 0, 5, 4 is also a point on the line. And so a different parametrization we could have done would have been, I'll call R2 of t, is going to be 0, 5, 4. That's a point on the line, plus a direction vector, -2, 6, -3. Here's another parameterization that we could do. W could be the vector, the direction vector from P2 to P1. So W is now going in the opposite direction. W is going to be the negative of V. And so a different direction vector that points along the line, that's parallel to the line, would be the negative of this direction vector to -6, 3. And so R3 of t could be, I'll just use this point up here, 0, 5, 4, plus t times 2, -6, 3, For all of these, I'm just going to assuming that we're writing all t for the values of t that are allowed. Here's yet another parametrization that could work. R4 of t is going to be the point, and I'll use 054. That makes much of a difference here. And I'm going to take the direction vector, I'm going to multiply all of the entries by 100. 200, negative 600, and 300. This is again a legitimate parametrization. You know, multiplying our direction vector by any scalar is going to result in a parallel direction vector. Let's say non-zero scalar, just so that we don't have trivialities here. So there are many possible ways to come up with this parametrization. Okay, so hopefully this convinces you parametrizations are not unique. Okay, so the last example in here is similar, but there's one little twist here. Parametrize not the line through 2 points, but the line segment between 2 points. So we have P1, we have P2, and we want to parametrize just the line segment between these 2 points. Now, let me come back here and let's start with this parametrization. We know this parametrization for all t is a parametrization for the line through these 2 points. So let me recopy this to negative 1, 7 plus t times negative 2, 6, negative 3. Let me make the following observations here. When I plug in 0 in for t, I get 2, negative 1, 7 plus 0 times negative 2, 6, negative 3. And this is going to be 2, negative 1, 7 plus who cares? 2, negative 1, 7. It's the position vector of our first point. So at times t is equal to 0, we're at P1. Okay. Now I'm going to plug in t is equal to 1 in here. I'm going to get 2, negative 1, 7, plus 1 times negative 2, 6, negative 3. And I'm going to get 2 minus 2 is 0. Negative 1 plus 6 is 5. 7 minus 3 is 4. And lo and behold, I have the position vector for this point t2. That happens when we plug in t is equal to 1. So at t is equal to 0, we are at P1. When t is equal to 1, we're at P2. So if we want to parameterize just the line segment from P1 to P2, instead of saying all real values of t, let's just have t runs from 0 to 1. So sometimes we don't want the entire line, we just want a particular line segment. We achieve that by changing the bounds on t.